In this video, we are going to talk about something called VSEPR theory, which explains the shapes that molecules make when they are formed. It's important for us to know what shapes molecules make when they are formed because it allows us to predict some of the reactions that they can have and some of the ways that they interact with other chemicals. Before you watch this video, make sure that you have watched my video linked below about how to do the 5-step method for drawing covalent molecules. VSEPR theory stands for valence shell electron pair repulsion theory. In the valence shell, which is the outermost shell of an atom, we have electrons that are available for bonding. Electrons that are individual electrons are available to make a bond. Paired electrons typically are not available to make a bond. But what we know is that electrons are all negatively charged and do everything that they can to get away from each other. Because like charges repel, they will always spread out in space as much as possible. We're also going to realize that unpaired electrons don't need as much space to spread out as a pair of electrons would need. So we're going to use the idea that surrounding an atom will be electrons, and those electrons will either be available in pairs that are unbonded or as electrons that are involved in making bonds. Once we've drawn a covalent structure and found the central atom, we need to find out the amount of areas of negative energy that are around it. These areas could be in terms of charge clouds or bonds or lone pairs that surround the single atom. So a charge cloud is considered to be a single, double, or triple bond. So any kind of bond that exists is considered one single charge cloud. Okay? So it's any bonding arrangement that we might have between two atoms that are holding them together. A charge cloud might also be a lone pair of electrons that are not used in bonding, or a single unpaired electron that we will find very rarely, but it does exist in some cases that a single unpaired electron may exist. Now I mentioned that the amount of space required around the atom is different if we're considering these charge clouds to be bond or pairs. A bond is a single, double, or triple bond and requires a certain area and space. A lone pair would be a pair of electrons not involved in a bond, or a single unpaired electron, which again is rare, but we would treat it the same as a paired electron. In a nutshell, we're basically looking at either we have a bond holding two atoms together, or we have a pair of electrons that's taking up an area of space. So as we look at a bunch of different molecules, and I'm going to show you many examples here, we're going to be looking for the different kinds of charge clouds. Are we looking at bonds or are we looking at electron pairs? Based on this, there are 13 shapes. And in university, you're going to have to memorize the names of these 13 shapes and the bond angles that form between them. So the simplest type of bond, the simplest type of molecule, only has two different atoms. And because there are only two atoms, it would have to be a linear geometry. There's nothing but a line between 2 points. But if we have more than 2 atoms, we get into all the varieties that we can talk about. Carbon dioxide is a great example of linear geometry. Linear geometry happens when we form a straight line between our central atom and the 2 terminal atoms. The bond angle between the central and the 2 terminal atoms is 180 degrees on either side, and that forms a molecule in a straight line. If I were drawing a molecule like carbon dioxide, after I'd followed my 5-step method and realized that around the central atom I have a charged cloud both to the left and to the right consisting of bonds. We have a double bond between this carbon and this oxygen, and another double bond between this carbon and this oxygen. There are 2 charge clouds there, both in the form of bonds. you notice that around the central atom there are no lone pairs. I can see that lone pairs do exist around the oxygens, but we're really only interested in what's going on around the central atom, in this case, the carbon. And because there are no lone pairs around the carbon, we would say carbon has 0 of them. So when there are only 2 bonds, 2 charge clouds, the furthest apart they can get is 180 degrees to be on opposite sides, and that forms a linear shape. Let's look at the possibilities that exist if we have 3 charge clouds around a central atom. Boron trifluoride is a first example of something that has 3 charge clouds. After following the 5-step method, I notice that I have a single bond on 3 sides of the central boron atom. We can see that we have 3 bonds and no lone pairs. The farthest apart in physical space that I can get any 3 bonds is to spread them out at 120 degrees. The bond angles between these terminal fluorine atoms would be at 120 degrees. The name for this type of molecule is trigonal planar. Trigonal meaning 3 angles, planar meaning all on a flat plane. So we would picture this molecule kind of existing like it was flat on a piece of paper, with 3 bars sticking out as far apart as they could get from each other at 120 degrees, 3 of which accounts for the 360 degrees in a circle. Another way to get 3 charge clouds around a central atom is to replace one of those bonds with a lone pair. How does that change things? In the molecule nitrogen dioxide, which is in the form of a polyatomic ion, you notice that you have 2 bonds and 1 lone pair. We see that we have a single bond there and a double there. Regardless of whether bonds are single or double, they're still considered a bond and occupy an area of space. Also, surrounding the atom is a lone pair. This lone pair also is occupying an area of space. In a planar type molecule, what we have done is we have taken around our central atom, we had 2 bonds, 3 bonds in the previous atom. We've replaced one of these bonds with a pair of electrons. We still can't get these to be more than 120 degrees between any 3 points. So you could almost picture this lone pair of electrons as a bubble in space without anything attached to it that occupies an area of space. We still expect between any of these there to be, though, a 120 degree bond angle. Although all we can see in this particular molecule is this part of it, because of course the lone pair isn't part of the molecule. We see a bent type structure, and we would call this to be a bent formation. Let's look now at what happens if we have 4 charge clouds surrounding a central atom. The simplest, of course, is to always have all 4 charge clouds be bonds. Methane, CH4, is a great example. Following the 5-step method, you would typically draw methane to be a flat kind of almost cross sign molecule. But in reality, in order to get all 4 bonds as far away from each other, they would occupy 3-dimensional space. In 3-dimensional space, the 4 bonds that we have would be a little tripod on the bottom with 1 molecule sticking straight out the top. We call this particular shape a tetrahedron, and this forms a tetrahedral structure. The bond angle in a tetrahedral structure is 109.5 degrees. It's a weird number, and all I can recommend is that you memorize it. Now let's start replacing these bonds one at a time with charge clouds to see how that would change the shape. In the ammonia molecule, we still have 4 charge clouds. We have 3 of them in the form of bonds, and we also have one charge cloud in the form of a lone pair. That lone pair is going to take the place of one of our original pieces of our tetrahedral structure. Remember, the tetrahedral was a little kind of a tripod sitting on the bottom with one of them going straight up. When we replace one of these bonds with a pair of electrons, what we find now is that we have so many charge clouds that this electron pair actually wants to occupy a bigger area of space. It actually forces the little legs of the tripod down and closer together. So now my bond angle has been reduced to 107.3. From now on out, what we want to remember is that charge clouds will occupy a bigger area in space if they're in the form of a lone pair than they do if they're in the form of a bond. And that's because we're starting to push things closer and closer together. Water is another example of a molecule with 4 charge clouds. In the water molecule, 2 of the charge clouds are in the form of bonds. We would also see 2 of the charge clouds in the form of lone pairs. Remember, the lone pairs want to occupy a bigger area in space. Again, thinking of our little tetrahedron, which is our tripod with our stick on top, that was the basis for 4 charge clouds. We have now replaced 2 of those sticks with lone pairs. So one here and one there. And remember, they occupy big areas of space, and they will try to squeeze these 2 sticks even closer together because lone pairs occupy a bigger area of space than a bond charge cloud would. The bond angle is further reduced to 104.5 degrees. Okay, let's look at some examples now when we're moving up to having 5 charge clouds. It's kind of hard to draw this, so you're going to kind of have to work with me a little bit in this example. We're going to start with 5 charge clouds where all the charge clouds are in the form of bonds. For example, in PCl5, surrounding the phosphorus, we have 5 chlorines. We have 5 bonds and no lone pairs. The best way for us to think about this is we're going to start with our plane in the middle where our central atom, the phosphorus, is surrounded as far apart as they can spread 120 degrees on a flat plane like a piece of paper, 3 of our chlorines. From there, we still need to add 2 more chlorines. So we're going to have one going straight up, out, and the other one's going straight down. In the picture that we have above, we have done our best to draw the 3 chlorines on the plane, forming the tripod, the planar part, at 120 degrees. And I show you that we've got one going straight up and one going straight down. So on the planar part, the bond angle is at 120 degrees. The bond angle between the straight up and the straight down would only be at 90 degrees. The name of this shape is called trigonal bipyramidal. You have a trigonal plane with a pyramid up and down. So this almost forms a pyramid up and a pyramid down, trigonal bipyramidal. 2 little 3-sided pyramids stuck top and bottom. It's a horrible drawing, but you're hopefully trying to get the impression of what I'm trying to show you here. As we go for more 5 charge cloud shapes, remember that we're going to try to replace a bond with a lone pair. And lone pairs will always want to find a place to be where they have the most space. Sulfur tetrafluoride is a great example of 5 charge clouds where one of them is in the form of a lone pair. In sulfur tetrafluoride, we have 1, 2, 3, 4 bonds, and we have one big lone pair wanting to occupy an area in space. 4 bonds and 1 lone pair. Where would the lone pair prefer to be? Well, it's going to have the most space in the planar part where the bond angle was at 120 degrees. So we're going to take one of the bonds off of the plane section and replace that with an area of space that those two electrons can occupy. Again, within a plane, we can't get more than 120 degrees of separation, and so we'll maintain that. What you have left from that is a central atom that has something up, something down, and then it will have two sticking out from the plane, and the third part of the plane will be that lone pair. We still have the 90-degree angle between top and bottom. And around the area of the plane, if we can imagine this being a flat part, between any two corners, we're going to have 120 degrees. This particular shape that you're seeing here is called a seesaw shape, because if we were to try to lay this molecule down along the straight post that we have going up and down, we would have these two arms sticking out that would rock back and forth, kind of like a seesaw. Let's try another one where we replace yet another one of these bonds with a lone pair. In the molecule iodine trichloride, we still have 5 charge clouds. You have 3 bonds, and you have a pair of electrons here and a pair of electrons there. So there's 2 lone pairs. There's still 5 charge clouds. Thinking back to our original shape, where is the best and most space that we can put a second pair of electrons? Again, the answer comes that it had to have been from the planar part. Again, remember the trigonal bipyramid where we had 3 different atoms sticking out on the plane, and then we had 1 up and 1 down from the plane? As we replace each of these with a pair of electrons, we realized that we could go to the seesaw by putting an electron pair here. We can go back again here, where there's still a fair amount of put place, and put another electron pair. These electron pairs occupy big areas on that planar section. What's left that we can see in red is a straight stick with 1 arm sticking out of it. Basically, it's the shape of the letter T, and we would call this type of molecule T-shaped. Can you predict where we would put the next lone pair in a 5 charge cloud scenario where we had a 3rd lone pair? That's right. It would also occupy a spot on the planar part from the trigonal bipyramidal. Surrounding the central atom, we would have 3 lone pairs of electrons. The other atoms, the terminal atoms, would have to go top and bottom. This again leaves us with a linear-shaped molecule. Xenon difluoride is a good example of a linear molecule. It's probably the first time you've ever seen me use a noble gas as a central atom. But as our noble gases get lower in the periodic table, as we get bigger and we occupy our D and F subshell electrons, we actually have more potential bonding sites, and it does technically become possible. Okay, so what are we going to do if we actually try to have 6 charge clouds surrounding a central atom? Again, we're going to start with all 6 charge clouds being in the form of bonds. Look at sulfur hexafluoride. This sulfur with 6 fluorines surrounding it has 6 charge clouds, all are going to be found in the form of bonds. Our best way to think about this is put the sulfur in the middle, spread the first 4 out on a flat plane as if they were on a piece of paper. And the next 2 will have one going straight up out of that piece of paper, and the next one going straight down as if out of that piece of paper. This would form for us a pyramid. You could imagine a pyramid with a square base and 4 flat sides. A pyramid with a square base that has 4 flat sides that we see going both up from the plane and down from the plane is called an octahedron, and will be the octahedral structure. Octa meaning 8. If each pyramid has 4 sides, there will be 8 sides to this shape altogether. Let's now use this octahedral shape to predict what happens as we remove 1 bond at a time and replace it with a charge cloud. In the drawings that you see above me, what you notice that all of my bond angles are going to be at 90 degrees. The flat plus part that's surrounded, the first four that surrounded the silicone, are each at 90 degrees. And then the one that's coming up out of the page and back into the page would also be at 90 degrees. So there's no advantageous place to put a charge cloud in comparison to a bond. In IF5, we have replaced one of my bonds with a charge cloud in the form of a lone pair. So we're going to have 5 of my charge clouds being in the form of bonds and one of them being in the form of a lone pair. It really doesn't matter where we put it because all of my bond angles started off at 90 degrees. So to make life easy, I'm just going to replace the lone pair at the bottom. The remaining 4 that were in the plane are still there. We cannot see the central atom in this molecule because it's hiding behind the front one. From the top, you'll see that there are the 4 different initial fluorines sticking out at equal degrees. There will also be one coming straight in and out of the page, sticking straight up. We can imagine this to be a 4-sided pyramid. There's the 4 different fluorines sticking away from the iodine, and one sticking straight up off the top of the page. What we're left now is with a square pyramid, a pyramid with a square base. Xenon tetrafluoride is a great example of replacing yet another one of those 6 charge clouds with a lone pair. In xenon tetrafluoride, we see 4 of my 6 charge clouds from bonds. We see 2 of my 6 charge clouds from lone pairs. So in this case, we've taken this octahedron. We've put one of those pairs of electrons at the top, one of those pairs of electrons at the bottom. What was left now is just the 4 remaining bonds as far apart in space as they can get at 90 degrees. These 4 would actually appear to be flat, as if smashed out on a piece of paper. They can't form up a little pyramid shape or a tripod shape like we have in the past because the electrons at the top and bottom are keeping them kind of smooshed together so they're flattened out on a plane. Because of this, the shape that we would call this is square planar. To try to name the shape of molecules that have multiple central atoms, you would actually have to describe the shape around each central atom and take a look at the bonds around it. In this molecule, we have 3 central atoms. There's carbons in 3 places, each of which are surrounded by charge clouds. The central carbon here has a charge cloud, has 1 pair of electrons on one side and 1 on the other. At this point, we are linear. The carbons that we see on the end are surrounded by 3 charge clouds. They have a charge cloud on 3 sides of them. Again, 3 individual charge clouds that surround an atom are trigonal planar. We have trigonal planar around the end carbons, and we have a linear around the central carbon. So we end up with shapes that are different around each individual atom. This chart is a better example trying to explain the shapes that atoms form around their different central atoms based on having 2 charge clouds, 3 charge clouds where they're all bonds, or one of those bonds is replaced by a lone pair, 4 charge clouds, again starting with 4 bonds, and then what happens as we replace those bonds with lone pairs, 5 charge clouds, or 6 charge clouds. This allows for the different orientations around a central atom. So if you've been curious about VSEPR theory, you can ask and I can post for you a digital copy of the notes that would go along with this. They're easy to look up as well online. This chart is an easy lookup to find the different shapes around the central part of an atom. And this is something that you're actually going to have to learn and memorize when you get to university. Understanding VSEPR theory is the beginning part of understanding the shapes of molecules. In the next couple of lessons in this extension that we take into AP Chemistry or first year university, I'll explain other ways that we can look about the shapes of atoms and molecules that they form, including some of the cases where following this pattern doesn't seem to work.